Okay, so we continue with our lectures on graph theory. Today we are going to discuss what is called acyclic graphs in the first part. So what is an acyclic graph? As the name suggests, a graph that does not contain any cycles. So they are called acyclic graphs, or a more commonly used word is a forest. So acyclic graphs are called forests. Now, so here is an example of a forest. If you want to look at this, so you can see this graph represented below does not have any cycles in it. So all the all the components of a forest are called trees. So components are the maximal connected subgraphs, right? If you remember. So you can see that there is this one component. Then there are these two single vertices, the 17 and 16 are components. Then there is this path on three vertices, which is another component. And then you have a vertex with several neighbors. This is another component. And there is a path again on four vertices. Right? So these are all examples of trees, and that together form an acyclic graph, which we call a forest. Okay, so here we have a forest. Now there is a special name for the this type of graph where we have one central vertex and every other vertex is a neighbor. Such a tree is called a star. And stars are also some important class of trees we will see sometime. Now, so this is an example of acyclic. Now, here is one theorem. Suppose you are given an acyclic graph, let's say F, okay? And assume that this forest has at least one edge, and you can have just isolated vertices. But apart from that, if you have just a graph with at least one edge, then this forest has at least two vertices of degree exactly equal to 1. Okay? So the vertices of degree 1 are called leaves. So in a tree, if you have a vertex of degree 1, they are called leaves of the tree. So how do you prove this theorem? Okay? So you want to show that given an acyclic graph with at least one edge, it contains at least two vertices of degree exactly equal to 1. Now maybe you should think about this for a few minutes. It's very easy to come up with a proof. But there are several ways to do this, but here is one. So we already looked at this kind of extremal questions. So take any non-trivial component of the forest, and then consider a maximum length path in that. So whatever is the longest path. So take given any graph, what you do is that you look at the longest path in this graph, and then we look at the endpoints of this. Let's say u and v. Okay. So you have this path uv, which is a maximum length path in one of the components, right? Any component that you are taking, and then look at the end vertices u and v. We are looking at non-trivial components, so there is at least one edge. Now, what can we say about the degree of u? Okay. So I claim that the degree of u cannot be more than 1. I mean, it has to be exactly equal to 1. So why is this? So if you look at the vertex u, suppose it has any other neighbor, right? If it has any other neighbor, let's say u dash, the vertex u dash cannot be outside the path, because if it is outside the path, we can get a longer path by starting from u dash to u, right? And then continuing on the path. So this will give me a longer path, but we started with the maximum length path. Right? So therefore, you cannot have any other neighbors. I mean outside the path. Now, if it has a neighbor inside the path, right? Then what does it say? Suppose this neighbor of you is inside the path, then you have some neighbor in the path. Then you already have the connection between these two vertices along the path UV, and then you have this additional which creates a cycle. But we started with the assumption that the graph is acyclic. So therefore, this is also not possible, which says that the vertex u must have degree exactly equal to 1. Now the same argument holds for v, so therefore u and v must be vertices of degree equal to 1. So this is true for any maximal path, so therefore we can show that the tree contains at least, any non-trivial forest contains at least 2 vertices of degree exactly equal to. Okay, so and this of course holds for we proved it for just a single tree, any non-trivial tree. So if there are several components, then you can say that there are several leaves in the tree, right? Okay, so here is the proof. Let F be an acyclic graph and T be a non-trivial component. Now consider a path of the maximum length in T, say P is equal to U1 to UK. Every neighbor of U1, as we mentioned, and of course UK also, lies on the path P, right? Because otherwise we said that there is a longer path. Now if there is a neighbor which is other than the immediate neighbor in the path, then there is going to be a cycle. So therefore the graph is acyclic. I mean therefore the vertices have degree 1 because the graph is acyclic, right? Okay. Now here are some here is a homework question. Show that the following are equal. So this is a very important result in the study of acyclic graphs. So these are the statements. Okay, first statement is that T is a tree. Okay, so given a graph T, right? The graph T is a tree. That is equivalent to the statement that there is a unique path between any two vertices of the graph T. And they are also equivalent to saying that T is a connected graph, but T minus E is not connected for any edge E in the graph. Okay. So for every edge, T minus E is disconnected, but T itself is connected. So in this sense, we can say T is minimally connected. So if the graph is minimally connected, then it must be a tree. And the graph T is acyclic, right? There is no cycle. But if you add any edge, right, which was not present, right? So suppose U and V are not adjacent, you add an edge U to V, then it creates a cycle in the graph T. If this is true for every non-edge U and V, right? So if UV is non-edge, you add it to it creates a cycle. If that is true for every non-edge, then we say that is also a tree. So these are all equivalent. So we have to show that let's say something like 1 implies 2 implies 3 implies 4 implies 1. So whichever way you want, you can show this, but show that these statements are all equivalent. So the proposition is as follows: a connected graph of order n, which means the number of vertices n, is a tree if and only if it has n minus 1 edges. Okay? So we are given that like the graph is connected, which means that any two vertices, there is a path connecting them, and it has exactly n minus 1 edges. Right? Now suppose we have a tree. Okay, so we have to show two things, right? Suppose that the given graph is a tree, then we have to show that it has exactly n minus 1 edges, and we have to show that if a connected graph has exactly n minus 1 edges, then it is acyclic. Right? That is what we want to show. So here is the proof, right? So let us first show that. Let us first show that if the graph is a tree, then it has exactly n minus 1. So that so because it is a tree, of course we know that it is connected, right? Now let us take an n vertex empty graph without any edges, right? And then add edges one by one. Now, what happens when I add an edge? When I add an edge, if I take two distinct components, so different components which are not connected by an edge, and put an edge between them, then these two components, because so each component, for example, I have this component and this component, right? If I take any vertex here and any vertex here, and then connect them with an edge, okay, then what happens? This entire thing becomes a component, because in this component I can go from any vertex to any other vertex because there is a path, right, by definition. And similarly from this vertex, let's say this is x and y, then from y to any other vertex in this component I can, right? Now to find a path from any vertex to any vertex in this big part, all I have to do is that take a path from the starting vertex to, let's say, u, then take the edge u to x and x to y, and from y to any other vertex that we have here, right? So this should give as a path between any two edges. So therefore, if I take two distinct components and put an edge between some vertices of these two, then I will get a connected larger component, right? So this is which says that if I add an edge between two distinct components, the number of components decreases by exactly 1, right? And of course, it cannot decrease by more than 1 because an edge only can connect two components. So if I start with n vertices, then when I add one edge, it can reduce the number of components by 1, right? So I start with exactly how many components? N components. Then I add one edge, it decreases the component by 1. Then I add one more edge, right? It decreases the components again by 1, right? If I am connecting two distinct components. Now, if I add an edge between the vertices of a component, it will not decrease the number of components. But it will create a cycle, right? So for the time being, let us not add such an edge, right? And let us see that we just keep on increasing the edges so that the number of components decreases every time. Now, if I do this, right, to maximize the and minimize the number of components, then because I start with n components, I need to add at least n minus 1 edges to make the graph connect, right? So every time I add an edge, it only decreases the number of components by 1. So I start with n, then n minus 1, n minus 2, etc. If it becomes 1, then I have added at least n minus 1 edges. So before adding n minus 1 edges, we cannot make the graph connected. So we need to have at least n minus 1 edges. Now, can we have more than n minus 1 edges, right? Right. So at least n minus 1 edges are required to make the graph connected. But suppose you add one more edge, right? So if the graph is already connected, and then you add edge between vertices of some component, then you automatically create a cycle because there is distinct path between two disjoint paths between these vertices, the edge and the path in the original. So therefore, that is not there, right? So therefore, we see that if the graph is a tree, which means that connected and acyclic, then it has exactly n minus 1 edge because it cannot have more than n minus 1 edges, because once it becomes connected, you cannot add any more edges. And to become connected, you need even we can make it more precise if you want. Now, here is another observation. that is something that we defined earlier, but we can define in a different way. Okay. So we define a rooted tree, right? In the earlier case, when we look at functional diagrams, we define rooted trees are trees where there is exactly one cyclic vertex. So those were called the roots, and then we had the rooted tree as this functional diagram. Now we can also give a rooted tree by the following. We have an undirected graph, and you just make one of the vertices as special vertices, okay, and call it a root. That becomes a rooted tree. Okay, so this is the natural, or the first way. I think people have come with the notion of rooted trees, because you take a tree and then consider one of the starting vertex or initial vertex or special vertex, which we call root. Okay. So you take any arbitrary tree, pick any vertex and make it a special vertex, say that this is the root. So that becomes a rooted tree, right? We can start from a vertex and pick any of the vertices to make root. So there is this graph that we get, right? This is a rooted tree where this vertex is special, right? And instead, I take this same graph and make this a special, then I get another rooted tree. Now, there is a one-to-one correspondence between the rooted trees that we come up like this and the functional diagram which is rooted. Because we observe that in the functional diagram, if you have a cyclic vertex, then every path from other vertices must lead to this vertex. It should all be coming into this, because this vertex already has an out degree, right? So it cannot have any other incoming edges, outgoing edges. So therefore, every edge to it must be incoming. Now, because of this, this vertex, its neighbors also must be incoming edges, right? So we can follow this argument and show that once you fix a root, right, then all the paths must converge to this cyclic vertex or the root. So that is how we get the functional diagram. Right? Now, so that rooted tree is exactly equivalent to this, because all we are doing is that, okay, whatever is, once you finish the root, every path converges, right? Basically, from every leaf, you go find a path to this vertex, which is directed path. So, because that is a unique way to do it, we see that there is a bijection between these. So therefore, we can now call any of these as rooted tree without worrying about which definition it comes from, and we can use it as it is, and we can go from one to the other and etc. So this is a simple observation. Now, what are the main questions that we are interested in combinatorial? It's of course counting questions. So here are some natural counting questions that arises. Of course, there are many more. I just mentioned a few, right? So one question is that what can we say about the number of trees on the vertex set V, let's say. So given a vertex set V want to Vn, we want to see how many distinct trees you can make on this, right? So with the label we want to Vn. Now the number of trees, let's say that where each vertex a degree is now specified. Let's say Vi has a degree exactly Di, right? V2 has degree exactly D2, etc. Now in this case, can we count the number of trees? Or if you say that the number of non-isomorphic trees on n vertex, because when you have labeled trees, there could be isomorphism between the corresponding trees, some of them, right? So if there are isomorphisms, when we don't want to count all of them, we want to just say how many trees are there which are equivalent under the isomers, right? I mean, distinct under the isomers. So how many classes are there, right, under this equivalence relation of isomers? So that is another question one can think about, right? You can ask number of rooted trees, number of acyclic graphs, right? All this we can ask about just the acyclic graphs. So these are all questions. Some of these we will try to tackle now, and some of these we can try to work out when we look at further topics like maybe the species and things like that. We might find an easier way to do this. But we will look at a couple of things at the moment. Now, here is one of the questions, right? So, so what was this question? That the number of trees with degree of vi is equal to di. So here is a theorem which explains our count. So number of trees on the vertex at v, where degree of vi is equal to di, is given by n minus 2 factorial over d1 minus 1 factorial. I think there is a missing into dn minus 1 factorial. Okay, so d1 minus 1 factorial, d2 minus 1 factorial, etc. dn minus 1 factorial, where the summation di is equal to twice the number of edges. We know that, right? The total degree is twice the number of edges, and therefore that must be equal to 2 into n minus 2, because the tree has exactly n minus 1 edges. So therefore, here is the formula that given a vertex at v1 to vn, and given that every vertex vi has degree is equal to di, we can construct trees only if, of course, summation di is equal to n minus 2. Otherwise, we cannot do that. And if this sum is equal to n minus 2, then the formula is given by n minus 2 factorial divided by d1 minus 1 factorial into d2 minus 1 factorial into dn minus 1 factorial. Okay, so now how do you prove this? Okay, so here is a proof. So what we are going to do is to use induction on n. So the base case, n equal to 1 is trivial, because there is no edge, there is one tree, and that's it. You can see that the formula holds. And for n is equal to 2, again there is a unique tree, right? What is the unique tree? The single edge, right? That is a tree. And this happens precisely when d1 and d2 is equal to 1. And in the other cases, right, d1 is equal to 2 and d2 0, we can see that there is no tree, right? This is something that you can immediately see. So therefore, again we can see that the formula holds. You just verify this. So once you have the base cases, let us assume that n is at least 2. N is strictly greater than 2. We have proved 1 and 2. And now suppose the result holds if the number of vertices is less than or equal to n minus 1. Right? So if the number of vertices is strictly less, then it holds. Now, what we do is that we take the set of trees on the vertex set v1 to vn with the degree of vi is equal to di. So collect all this, right? So given this sequence d1 to dn with the degree of vi is equal to di, we look at the set of all trees that we can construct on the vertex set v1 to vn with this property. Okay. So consider the set and call it as x. Right? So we can observe that the di cannot be 0 for any n, right? Because we are talking about trees, and because it is connected, like this is one way to look at this, right? We cannot create any tree if di is 0 for some right? Because it cannot be connected. As far as we are not looking at the trivial tree where n is equal to 1. We are assuming that n is strictly greater than 2, right? So therefore we can think of this and say that, okay, now di cannot be 0 because the graph is going big. So there is no tree possible. So if di is 0, we will see that, like, in this formula, right, we will get di minus 1 factorial. That becomes a problem in our definition, so therefore it doesn't make sense. So we will say that that is not possible. Right? So therefore, di is equal to 0 is ruled out. Now, so suppose dj is equal to 1 for some j. This we can always assume. Why? Because suppose for every di, right, was greater than or equal to 2, then we have n di's, right? So therefore the sum is going to be equal to 2n, it's greater than 2n minus 2. Right? If every vertex has degree at least 2, there are n vertices, total degree will be more than 2n. So therefore we know that since di is not non-zero, it must be equal to 1 for some vertex. So let us say dj is the vertex whose degree is 1. Okay, that's at least 1. Okay. So let us fix this particular vertex dj whose degree is going to be 1. Now what we notice is that, like, by the definition of the way we construct this, right, d of vi is equal to di for all the graphs in x. Right? So which means that for the graph that we are going to consider in x, the degree of vj is going to be always 1. Right? So vj is going to be a leaf in all the trees in x. Okay. So what we can see is that all the trees that we are considering, vj is always going to be a leaf, which means that it has exactly one neighbor, right? Now we collect these neighbors, right, and then make another set like this, right? For every tree in A, let AK is the set of all trees such that Vj Vk is an edge in the tree, right? Because Vj has a unique neighbor, it is going to be exactly 1k for a given tree, right? So that k, it will be different from j because there is no loop in our trees, right? So therefore, for every case, we can consider the possible case, right? So AK is basically the set of all trees such that Vj Vk is in the edge of T, right? So so we are basically now collecting with the index of the neighbor of this particular vertex Vj. That could be different in different trees, right? But of course, the degree of Vj is actually equal to 1, but the neighbors could be different in each of the different trees. Now, because we, this AK must cover, right, all of A in at least some of these cases, A is going to be disjoint union AK. And this is disjoint union because you cannot have two different case intersecting, right? Because there is a precisely unique neighbor for Bj. So therefore we get a disjoint union of AK which is equal to A. Now let us pick some K which is different from J, of course, right? So so what we do is that we are going to delete this single degree vertex which is a leaf, right, Vj. Once I delete the vertex Vj, what happens, right? Because it's a leaf, it is not connected to anything other than its unique neighbor. And every path from this vertex, because the tree is connected to every other vertex, is actually going through the neighbor, right? So if I remove this particular leaf, the remaining graph is still going to be connected. It's something that you can immediately see from the structure of a tree. Right? If you remove the leaves, it does not affect the connectivity of the remaining part. So therefore, we are going to get trees on the vertex set v minus vj. Right? So v1 to vj minus 1, then vj plus 1 to vn. Right? So on n minus 1 vertices, we get trees which are again connected. And what is the property of the trees that we obtain this way? For all the trees, degree of vi is equal to di, right? Because we have not changed the degree of anything except for vk, right? So for I not equal to k, degree of v is actually equal to di. Now, once you Once you observe this, what happens to degree of bk? Degree of bk changes exactly by 1, right? It reduces by 1 because we just removed one of its neighbors. So it is going to be dk minus 1, right? Now we can see that there is a bijection between the trees AK that we are looking at and the set of trees that we obtain here by deleting this, because we precisely have the same thing here except we removed one leaf. And if you have anything here with this degree sequence, we can also add a leaf, make it adjacent to one of the vertices, right? And then we will get a tree in A, right? So it must be present in one of the AKs. So therefore, there is a one-to-one correspondence. So the cardinality of AK is precisely the cardinality of the trees that we obtain this way. Now the trees that we obtain this way is all trees, right, that we can get where the degree sequence is given here, right? All trees on n minus 1 vertices where the degree sequence is given here, right? D of VA is equal to DI, I not equal to K, and degree of PK is equal to DK, right? So now we can use index, right? So what is the induction, right? So well, whatever is the number of vertices, right, which is n minus 1 in this case, minus 2, right? N minus 2 becomes n minus 1 minus 2 factorial. So we have n minus 3 factorial divided by, right, the degree sequence whatever it was given, that di minus 1 factorial etc. into each of them, right? So now here the degree, the first one is degree of vk is dk minus 1, so that minus 1 which is dk minus 2 factorial, then product over all the other remaining terms, right, di minus 1 factorial for I not equal to j and k. Now this is just manipulation now, right? So this is the cardinality of AK, and now that is equal to n minus a factorial into dk minus 1, because I just multiply by dk minus 1 factorial and dk minus 1 on the above and below, right? So therefore this becomes dk minus 2 factorial into dk minus 1 becomes dk minus 1 factorial, which I can take inside, right? I can take it inside, and then the numerator at that time is remaining, right? So that then I will get n minus 3 factorial into dk minus 1 into product I not equal to j di minus 1 factorial. Now here is something that we should observe, that so I not equal to j, right? There is one term still missing from our general formula, but what is that term? That term is dj minus 1 factorial, right? But we know that dj is equal to 1, right? Degree of dj is dj, which is equal to 1. Because dj equal to 1, dj minus 1 factorial is 0 factorial, which is also 1. So I can as well put that term inside. Doesn't make any difference because dj is 1. So then I can just write it product over all I di minus 1 factorial, because doesn't matter whether I add that particular case of dj. So therefore I will get this without I equal to j, so I can even write it this way. Now, so what is the cardinality of A? Well, it is the sum over all k different from j, cardinality of AK, right? By definition here, right? It's the union over all k, AK. And what we have? Well, summation over all k not equal to j, summation, equal to j, n minus 3 factorial into dk minus 1 by product I not equal to j and da minus 1 factorial. Now, we can write this as we just mentioned in the previous slide, right? We can write the summation n minus 3 factorial into dk minus 1 by product over all I da minus 1 factorial. Now, since these terms are not depending on k, we can just take it out. So we get n minus 3 factorial by product over all I da minus 1 factorial. Summation k not equal to j dk minus 1. Now, what is this sum? Well, this is the sum of the degrees where k is different from j, and we can see that it is actually equal to n minus 2, right? So because we are basically saying that summation dk minus, so summation decay is 2n minus 2, then we have like minus 2n minus summation decay is k not equal to this. This is 2n minus 3 minus n minus 3 minus n minus 1, which will be n minus 2. Right? So this is equal to n minus 2 factorial by product di minus n factorial. So this gives us the induction, and therefore we show that this formula is true by induction. Right? So the number of trees on the vertex at b1 to bn, where degree of di is equal to fixed number di, is given by this, provided summation is going to be 2n minus 2. The degree sum should be equal to twice the number of vertices. Okay, so we have proved that. Now, since we have this, we can use this to find the number of all trees, okay, on vkm, because for each degree sequence, now we know how to find it. So you can sum over all this thing, we can get the. So that is a homework for you, right? Show that the total number of trees on v1 to vn is n raised to n minus 2 by using the above result, right? That for a given degree sequence, we have this n minus 2 factorial by product di minus 1 factorial. So that sum should be equal to n raised to n minus 2, right? So show this by using the previous. Now again, once we have this, we can immediately show that the number of rooted trees on the vertex at 1 to n is n power n minus 1. Okay, this is also immediate consequence. Once we have this, this is easy.